All right, so today's class we are looking at topic 5, which is portable power. So we will be looking at batteries today. So batteries are able to transform chemical potential energy into electrical energy. And we're going to talk about electrochemical cells. These are devices that can generate electrical energy from the chemical reactions that are occurring inside of it, or they're using the electrical energy supplied to it to facilitate chemical reactions inside of it. So basically, they're capable of converting chemical energy into electrical energy or vice versa. So here is a diagram of an electrochemical cell. So inside of an electrochemical cell, you will see two metal electrodes. So this one and this one, those are called the metal electrodes, and they are surrounded by an electrolyte. So the electrolyte solution here, labeled right here, electrolyte. That electrolyte, it's a solution. It's a substance that can conduct electricity. In a wet cell, it's a liquid electrolyte. So such as car batteries, they will contain several wet cells, and it is a liquid electrolyte. And then dry cells, they have a paste or plastic or ceramic solid electrolyte. All right, so that's what a typical electrochemical cell contains. So we've got the electrodes and we've got the electrolyte. Okay, so next is taking a look at what is happening inside of it. So when the cell supplies current to a circuit, atoms of aluminum, so in this case we have an electrode made of aluminum and an electrode made of copper. So in this case, atoms of aluminum become ions and they go into the electrolyte solution. So what's happening is this aluminum strip will slowly start to disintegrate. And a similar process occurs in every electrochemical cell. One electrode is consumed as the cell operates. So in a wet cell, there's two metal strips. Like I said, here and here, those are referred to as electrodes. They're placed into the electrolyte solution. It's usually like a mild acid. One of the strips is almost always made of copper. The other strip, it may be aluminum, it may be zinc or nickel. And each of those electrodes are going to react differently in the electrolyte. So this acidic electrolyte is going to start eating away this electrode. So again, it could be aluminum or zinc. And it'll leave behind electrons, shown here, that give it a negative charge. The copper electrode here is going to be positive. It's not going to get eaten away. So the electrons are going to travel from this negative terminal. It's attached to this zinc or aluminum electrode. It's going to go through the circuit and it'll move on to the positive terminal, which is attached to this copper electrode. All right, so this current, it returns to the copper by that wire, and that is how electricity flows. Once this electrode, this aluminum one, or if it's zinc, once it's completely eaten away by the cell, it will no longer create electricity. If it's a dry cell, this one's a liquid. If it's a dry cell, it will work pretty much the same way, but instead of a liquid, the electrolyte is in the form of like a paste. So that's a benefit of a dry cell, is you can move it around in different arrangements, whereas if it's a wet cell, it has to be kept upright, all right, so that there's no spills. Okay, next, we're just looking at potential difference. So the chemical reactions in a cell will determine the potential difference or voltage that the cell can create. So usually single cells produce about 2 volts, So to obtain higher voltages, these batteries will contain several cells and they're connected in series. There's two different cells. There's a primary cell and there's a secondary cell. A primary cell is one that cannot be recharged. So the amount of chemicals it contains determines the total amount of electrical energy that it can produce. So if it's a large D cell, it'll contain more chemicals than a small AA cell. So that D cell will have a longer working lifetime than that AA cell in an identical circuit. So here, for example, this is a 9-volt battery. It contains six of the small 1.5 volt cells, and they are connected in series. And then we would have a secondary cell. These are the type that can be recharged. So they are rechargeable. They use chemical reactions that can be reversed. So in a recharger, electricity gets forced through that dead cell and it rebuilds the original chemicals, and then it allows the cell to be used. Right? But it still has a certain lifespan. Right, these are some different types of modern cells and batteries. You can take a look in the textbook as well. We have a zinc carbon cell, this is an alkaline cell, a zinc air cell, a lead acid cell, nickel cadmium cell, this is a nickel metal hydride cell. And then here's just a chart, just going through whether they're primary or secondary. So we can see here the lead acid, nickel cadmium, and nickel metal. Those are secondary cells. We can also see if they're dry or wet. You can see which is the positive electrode, which is the negative electrode. We can also see what is being used for the electrolyte in the chart as well as in the diagrams. So uses are shown here. For example, zinc carbon, you would see them in like flashlights, portable radios. Zinc air you would find in like calculators and watches. Lead acid in cars, motorbikes. Nickel cadmium you would find in like shavers, laptops. Nickel metal hydride you could find in like laptops, cell phones, and so on. Pros and cons are shown here as well, if they're efficient or not. So like a zinc carbon, it's not very efficient at low temperatures. Alkaline, they can last longer, but they are expensive. A zinc air has high energy. Lead acid, it's very heavy and it contains a corrosive liquid. Nickel cadmium, you're able to recharge it hundreds of times. A nickel metal hydride, it's less toxic and it does have more energy density than the nickel cadmium. It is rechargeable. So yeah, lots of pros and cons you can see there for those different types of cells. Okay, so I'm just going to pause here.